Hello and welcome to Simulation TV. My name's Sean Gedman, and today we're going to go over some Autodesk Moldflow design principles. So what are design principles and why use them? Design principles are just basically some tips that we'll give you based on general theory and practices out there that'll help you when evaluating your part design. And why we do this is we don't want to be throwing a dart with our eyes closed. We want to have some type of theory behind what we are doing in our simulation. So hopefully this will help you in these terms. So first one is unidirectional flow pattern. So basically what we're looking for is just trying to keep our flow consistent. You can see this first image is we have more of a gate location, a center apart, so we have different flow orientations going on here. So this could cause problems with stresses, deflection, and even some flow marks when you have a situation like this. So in a lot of these cases, uniformity is going to be the key objective. This one is a lot more uniform. It's kind of uniform orientation, a lot more uniform shrinkage from region to region in the part. So this is one of the design principles for you. Another one will be flow balancing. So we have a couple runner layouts. This one is a naturally balanced runner system. Some even call this a geometrically balanced system. And what this is doing is, you can see it's an H pattern. All the flow lengths are identical to each cavity. And what this does is make sure that each cavity in this 8-cavity tool that you see is seeing the same pressure and temperature history and filling at the same time. So repeatability between cavities. Another way to balance flow is the artificial balance runner system here. And essentially what this is doing is the flow lengths are not identical to each cavity, so we're basically inducing a hesitation into the cavities with the shorter flow lengths to help balance fill. Now, this is going to basically help us achieve a uniform pressure and time for the most part, but not the most desirable way to balance your feed system because, again, we can have quite a bit of scrap here in larger cavity tools. You can get quite a bit high pressures typically in smaller parts. So one way to do it, but not the most desirable. Constant pressure gradient. So you want to keep an eye out here for any spikes in your pressure. And in this example here, you can see everything is filling uniformly in the part. And then we get to that little tab at the end of the filling. And what happens is the flow front shrinking, all the flow is being directed to that section of the part, and you're getting a spike in the pressure. So we want to avoid situations like this if possible. Other things to take a look at would be maximum shear stress. So you want to be aware of the critical level, and what is a critical level? That'll be dependent on the material you're using and the application. So, optical parts might be a little more critical of this than maybe a children's toy. We do give you some guidelines in the material database under the properties of each material, but just keep in mind that these are general guidelines. So we're going to say an ABS material has a shear stress limit of 0.3 megapascals. If you want something a little more exact, then you might want to discuss this with your resin supplier. And of course, this will degrade some of your mechanical properties in the part if you exceed this. Uniform cooling. We want to keep an eye on this for several reasons. So in this example, you can see that we have a flat plate. It's hot on one side and cooler on the other. And what happens is that warmer side is allowed more time to shrink. So we get kind of a tensile force there, and it bows towards the warm side. So we want to try to avoid this and be mindful of this at least. Kind of taking that a step further, you can see something here that we typically refer to as corner effects. And that's the same thing, but maybe in a little more complex. So you're looking at here, we have hot core right on those inside corners, which is something we would typically expect. And what that'll do is the inside corners will shrink a little more and cause those edges of the box to bow inward. So in this case, you know, we need to maybe add additional cooling in that core, think about a beryllium copper insert possibly, but simulation again is going to give you a chance to experiment with this and figure this out hopefully before you cut your steel. Weld meld lines. So obviously if we can eliminate them, we should. You can't always eliminate them, but if you can't, let's position them in, let's say, areas that aren't as sensitive to having them there, such as in this example we have a hole in the part. If that's a place where maybe you're going to bolt the part to something else or a snap fit, it could weaken that area and you want to be mindful of this. And you can see we have a meld line and a weld line. So a weld line essentially is where two flow fronts are meeting directly with one another. Meld line, still two flow fronts meeting, but typically at a larger angle. So their meld lines are a little stronger, but still you have to watch that for not only structural concerns, but also cosmetic. Hesitation. So again, you want to be mindful of this and watch. If you can, ways to limit hesitation would be to make your wall thickness uniform. Naturally, that would help. You can position your gates far from thin features, or you can fill a little faster, because in this example you'll see the top one we gated near this thin rib, and what happens is, you know, like anything, plastics will take the path of least resistance. So the polymer is going in the gate, it's starting up the rib, but the main body is thicker, so it will take the path of least resistance and pause basically in that rib. And you know, depending on how fast you fill this thing, that flow front in the rib could be frozen off by the time it backfills and tries to fill it, and then you get a short shot. In the case of the part on the bottom, we're filling away from the rib. You still see some hesitation, but you know, we're passing that rib, filling the main part body, and then it's backfilling into that rib. So that's one of the reasons why we say maybe gate away from those thin features if you can't get it, or fill faster so it's not sitting stagnant in that rib section for too long and freezing off. Underflow, what you want to do, you want to avoid this as well. And basically what this is a change in the flow direction between the time an area fills and at the end of fill for that part. So in this case, you have this circular part with a little tab off the end. So what's happening is everything's very uniform, it's filling, and then all of a sudden we hit that tab and everything is diverted up towards that tab. So you have quite a bit of mix in orientation, and you can see here the blue is good, and you can see our fill pattern, contoured lines overlaid with the orientation, and you see our perpendicular, that's good. If you start seeing something that's starting to run parallel, that's not good, because it's shifting up towards that tab in this case. So be careful of that. Flow leaders and deflectors, these can be useful tools for you. So keep this in mind if you are having problems with something like this part here. You know, we're gating it on top, and naturally the shorter flow paths are going to fill, and it's going to racetrack around. It's going to fill over the short sides, racetrack around, and cause a big air trap on that one side of the part, or both sides of that part there. So what we can do is use a flow leader, which is a subtle thickness increase, and or a flow deflector, which is a subtle decrease in the wall thickness. And what that does is just allows the flow to be promoted along that longer flow lengths, and it delays it in the shorter flow length. So you can see in this example, the top one, uniform wall length, we have this air trap. On the bottom one, we put some flow leaders, flow deflectors, to promote flow or retard it in certain areas. And you can see it now fills this box a lot more uniformly. There aren't, say, weld lines in that location or air traps now. So something to keep in mind. Controlled frictional heating. This is something that's often overlooked as well. So what you typically do is when you're running your molding window analysis to determine your optimum melt temperatures, things of that nature, you're optimizing it off of the part. When you add a feed system, that's going to introduce shear heating. So what happens with that is the part ends up getting melt that is quite a bit higher sometimes than we intend it to be. In this example, you see 10 degrees Celsius. So what you might want to do is, if your goal was to, let's say, run this and then adjust your melt temperature so it accounts for shear heating. You'll probably run a melt temperature a little lower than you initially predicted, so we can account for that shear heating. Thermal shutoff, also gate freeze. This is something you want to keep in mind. You don't want to be any less, your feed system to be any less than 80%, or take any less than 80% of the actual gate freeze here, because what happens is you can run into packing issues. Your gate will freeze off before you can pack the part. And again, you don't want to go more than 200%, because then your feed system's going to start controlling your cycle. So in this image here, you can see the part on the right. That is a good setup. The one on the left, you can see the fill time is over 3 times, or the freeze time for the gate region there, runner system, is over 3 times what the part is. So the feed system's going to control the cycle here, and you're wasting cycle time. Acceptable runner cavity ratio. So this is just volume. Naturally we'll try to run a feed system with the minimum amount of material volume that we can. So that's what we mean here by design your runner system with high pressure drops. If your machine can handle it, we can shrink those feed system legs down and minimize the volume. And the typical guideline is, we want that runner volume to be roughly 20% or less of the overall part volume. In this example, our artificially balanced system, you can see the part volume is actually 85%. The feed system volume is actually 85% of the total shot volume here. And that's all we have for the design principles. Hopefully you've learned something today, and have a great day.